Okay, I'm Rosanne Rademacher. This is Chaipat and Rosanne. We like to work together, so today we're also going to present together, okay? So what we will try to convince you of is that memory reports are biased, but this is a good thing, okay? So the big question that we're trying to answer here is that what if these biases that we see, and we will talk about what they are, right, are actually adaptive implementations of using an available reference, like any available reference. And again, this will hopefully become clear, right? So this will be a journey in two parts. We'll talk really fast, so strap in. Okay, first, my memory is biased. So this is a really old study where we had a subject remember a random orientation, and then they used this method of adjustment to give a reply at the end. And there was a distractor during the delay, irrelevant, that had some offset, some fixed number of offsets relative to the target. When we look at the data, we plot the mean of the responses that subjects give, and on the x-axis is the difference between the target and the distractor. We see that there's an attraction towards its distractor, even though it's totally irrelevant, right? To make matters worse, if we look at the variance of the responses that people give, we see that the target and distractor are the same. Actually, there's a small improvement in performance, or like reduced variance. And if they become very different, then they are a little bit noisier in their responses, these subjects. Okay. But you might say there were actually statistical dependencies between the target and the distractor, because there was a fixed number of offsets that you showed. Okay, sure. So we try this again. Now we use random offsets between the target and distractor, and we see the same thing. So there's attraction towards this irrelevant distractor, and people are better when the distractor matches the target, and they get worse when it starts to deviate more. And look, I think this is kind of cool, right? So on top, I have the bias now. And when we look at the point where the bias is maximum, or maximal, let's say, the variance is actually pretty much the same as in trials without any distractor at all, okay? So this doesn't seem to, even though this bias is quite large, like in an order of 1, 2, 3 degrees, no matter how we test it, there seems to be really no impact on the noisiness of the responses of subjects. Okay, so memory is biased relative to these irrelevant distractors. Now you're asking this, right? Tell me more. That's what we're going to do. So the next thing we observe is that memory is actually biased relative to things in the world. Like, it doesn't even have to be a distractor on the screen. It could just be the screen itself. So what do I mean with that? So we have all this visual context. For example, this is the Frankfurt skyline. There's lots of orientations here, so vertical, lots of horizontal, and that is kind of true for the natural world in general. And this is hypothesized to lead to these very well-known distortions in orientation recall. So on the left is what we know is the oblique effect. So people have better performance at the obliques, so a lower discrimination thresholds. They are more precise in recalling these kinds of orientations. And they're worse, so better at the cardinals, worse at the obliques, okay? Then on the right is what we call the repulsion effect. So if you show an orientation that's a little bit tilted away from one of these cardinal axes, people are going to report this tilt in an exaggerated manner. So because we know the natural world has a lot of vertical and horizontal orientations, these are overrepresented, that these two things, these two distortions, kind of must stem from a common mechanism, right? Well, maybe not. So what we wanted to do is to disentangle this. So we had some clues that this may not stem from a common mechanism. So how are we going to test this? It might seem strange, but it's very simple. So bear with me. So usually your head is upright. And real world vertical and horizontal are aligned with, let's say, these cardinal axes and the way that they're presented on the retina. But we can pull these apart. We can dissociate these two reference frames. So if we have subjects tilt their head, now the cardinal axes relative to their eyes, to their retina, are tilted relative to real world vertical and horizontal, okay? So the oblique effect we kind of know is this hardwired thing because you just have more neurons dedicated to vertical and horizontal. So if you tilt your head, you would expect that to rotate with your head. So this is a task, stupid simple, random orientation, short delay. They do this method of adjustment to report the orientation. This was 5 days of testing. So again, I just want to highlight these wonderful RAs who collected all the data. You've seen a few on them on some slides already. Okay. what do these data look like? So this is an example subject. So we collected lots of trials. So this is actually just the raw data. And what you can see already is that these errors are not really uniformly distributed, right? Around zero, around no error. So we can take these two summary statistics. First, we can look at the variance of these responses. And what you can kind of see is these two bumps. So variance is lower at the cardinals, and it's higher at the obliques. So we know this. This is the oblique effect. We can look at the mean of responses, and we see this sort of characteristic repulsion away from cardinal. So we have this repulsion effect. Now, what happens when a subject tilts their head? You can already see in the raw data it looks different. When we look at the variance, again, we just see this oblique effect. And so on the x-axis, by the way, now I'm plotting this in retinal coordinate frames. So you see that horizontal and vertical, these are the teal lines, are shifted 45 degrees. So h is horizontal, v is vertical in the real world, okay? So the oblique effect tracks the retinal coordinate frame. But if we look now at this bias is shifted pretty much by 45 degrees. So this means that the bias is relative to real world vertical and horizontal. So what does this look like across all of our subjects? And this is just to highlight kind of what I already showed you, is that this oblique effect really just sticks with the retina. It doesn't really change much. But when we look at this bias and we compare this between head upright and head tilted, you see that this is 45 degrees translated, basically. Now, what happens if we take some of this context? Oh, wait, no, that's not what I'm going to say. I just want to show you some of the distributions. So at the cardinals, you see that these distributions of errors that people make are really punctate. At the obliques, they're much noisier. But one really cool thing is that when you look close to the cardinals where you get this repulsion, this is not just a shift of the errors. It's really a warping. So there's a really strong skew here in the responses. Okay, now we're going to take the reference frame away. So instead of a rectangular screen, we're going to use a circular screen. We use an Oculus for that. So there's no more visual reference to vertical and horizontal. And what do our data look like? Well, the oblique effect is still there, right? And it looks pretty much the same. And it should be, because this is hardwired. We assume this is pretty much hardwired. The repulsion effect, however, looks quite different. So it's much reduced. So without this external reference frame, it's not quite as clean. And so this shows that taking away this reference frame really messes with this bias, but it doesn't with the oblique effect. So do these two stem from a common mechanism? We would say, no, that's wrong. That can't be, because we can dissociate them in so many ways. All right, so far I've shown you that memory is biased by these irrelevant distractors. Why would it do that, right? And to make matters worse, you would think that memory is biased relative to just stuff in the world, like a rectangle, or what you know about vertical and horizontal. So yeah, what the heck, right? What's happening here? Memory seems to be all over the place, biased by all kinds of things. But then Chaipat came in with a pretty brilliant idea.
Yes, so are we trying to see if the memory also biased to other items in mind as well, not just the context of the world or the things that happen in the past or in the future. So let's imagine that you're trying to remember of these dogs. You might think that, because you're trying to remember so many similar dogs, that your memory could get warped, that they become more similar in your memory. But let's imagine that one of the dog is your dog, your favorite dog. What you want to do instead is not allowing them to be more similar to each other, but you might want to push them apart and make a repulsion bias in your memory so that the memory become, you can stand out. And that might especially be true if you're trying to remember a lot of more similar dogs, even more similar. So we want to test this hypothesis and say, if the repulsion bias is actually adaptive, that might, you may see stronger repulsion when you're trying to increase signal to noise. So you can manipulate this two signal to noise ratio by manipulate two of these. One is the noise in the system. So you can imagine that if the encoding is become noisier, then you might need repulsion to keep them apart. Or you can test whether you put these two memory color apart, then maybe up to the point you no longer need repulsion. But if you reduce the color similarity, make them more similar with each other, maybe the repulsion will come back again, right? Then you can imagine that up to a certain point, you cannot have, always have repulsion, because up to the point that they're no longer discernible, then you come backtrack to each other. So we test this hypothesis by just do two items memory test and do method of adjustment with color memory. Then you can manipulate encoding time, 3 different encoding times, and also 5 different color distances. So here you're looking at, the plot, 3D plot that I'm plotting the repulsion bias. In this case, it's just a number of response that's away from non-target, non-probe items, right? If it's symmetrical, then you expect to be 50%. If it's more than 50%, in this case, it signifies repulsion. As you can see here, that you see repulsion at different degree at different condition. Here, if you look at 50 millisecond encoding time, you see maximum repulsion at 45-degree color difference. But if you increase the encoding time a little so that the noise becomes less so, then you have to move them further closer to each other before you see the similar repulsion. And that's even more so when you increase it to 500 milliseconds. So what you're seeing here is the way to manipulate signal-to-noise ratio and see that you need a repulsion bias when they are more overlapping with each other. But here, what we're manipulating is this color similarity and encoding noise, but we are talking about memory noise. So maybe you want to also manipulate memory noise as well. So instead of, you pick the one that have the maximum repulsion, it's 150 millisecond encoding time, and manipulate delay interval this time. And the thing is, if you have to remember it for longer, then the noise in the memory will get accumulated, then maybe you see stronger repulsion as a function of delay. And here, just a manipulation check, you see that the performance kind of get worse over time, which you kind of expect. But interestingly, you also see stronger repulsion bias as the delay increase. And to check whether, this repulsion bias is just, some lazy strategy that people use. So you might want to also check at the individual level whether this repulsion bias is found in a better or worse subjects, right? So you can plot these two things together. You can plot performance in general on the x-axis and then bias on the y-axis. As you can see here that the people will have stronger repulsion, all the dots on the upper corner, it's the people will have less noise in the memory. So in general, I think we show that the bias is adaptive in many ways, and if you are interested, we also have 5 more experiments, 3 in supplement and 2 models in the paper. So memory is biased. It's relative to irrelevant distractor, as in the first part, also in the world center reference frame, and also to one another in the memory. So we think that the bias reflects anchors of many kinds of contexts relative to whether it's relevant or irrelevant, whether it's happened in the past or in the future, in the current moment, and it helped to stabilize memory. And lastly, I want to thank all of my students in the lab, and also RedMaker lab people are awesome. You want to say something to them? And also awesome. Our collaborator here.
They're awesome, I can confirm that. Yeah.
Okay, great. Thank you.
Thank you so much, and we have some time for questions, so please go ahead. Yes, Joey.
Thanks both for the wonderful talk. It's very interesting, and I wonder about how, I'm trying to wrap my head around it, and for the last bit you showed, from this, for the oblique effect, right, according to Wei and Stocker, the repulsive biases comes from the asymmetric likelihood function, right? And that's basically the encoding phase. But here you show for memory, there's also the repulsive bias. So how do you, do you think that this efficient coding can happen not only in perception, but also in memory? Or how is that, how could this be possibly implemented in the brain?
Yeah, so when we say that these two are assumed to stem from a common mechanism, that is a direct reference to the Wei and Stocker papers, because they do use the sufficient coding idea and saying that the prior informs both processing parts, right? So we think that must be wrong, right, based on our data. Why it's wrong, we don't know, and that's why we've been sitting on this data for a very long time, plus pandemic, right? But where does this happen in the brain? I think that's very much an open question. So we also have a data set that we're actually currently working on where we're doing pretty much this experiment, but with EEG. And so one of our hypotheses, but this may be totally wrong, right? one of our hypotheses is, let's say like your head is tilted, you have this visual input, the feed-forward stream kind of must be tied to the retina. But then anything that happens after that might be integrating this influence of knowing where your head is in space, and that's when you might see like a world-centered reference frame appear. But like tentatively, we have these data, we're looking into it right now, we might have an answer of VSS.
Thank you so much.